As I told you, today we are going to discuss that LaSalle's invariance theorem. Some people also write it this is this LaSalle's invariance theorem. How this is beneficial? So if you are still not aware, then and have not yet watched the previous video in a very minutely watch the previous video, I would request you to at least play the first 10 to 15 minutes of the previous video. Before I started mathematical rigor, what I discussed, that is very important to understand, that why do we need at all another theorem. Like a bunch of theorems can be studied, but it is not our objective to study a hell lot of theorems and means have a feelings like, oh, we are the mathematicians, but we must have certain understanding that why do we need it. So here the statement of the theorems, without wasting time, let me write: let omega belongs to, or rather omega contained in D, be a compact set that is positively invariant with for let we define a function v there is no restriction on v to be positive definite, right? Let v d to r. So how to define v, or means what else we are expecting from v? V must be continuously differentiable function. Just let me check whether it's recording. Yeah. Differentiable function. In some literature, you may find that v is a C1 function. So don't get confused with this C1. This C1 is not this C1. This is C, means this is a complex number. C1 means complex space of dimension 1, and this C1 indicates a function that is having continuous first order partial derivative. That means if you take the first order differentiation of this v with respect to its whatever variable you will consider, with respect to that, if you differentiate v, then the first order differentiation with respect to that independent variable is continuous. So if we find any function that is having second order continuous, then we can write it C2. Anyway, so in some literature you will find that V is a C1 function, or we can say that continuously differentiable function. If it is C2, then continuously second order differentiable function, continuously nth order differentiable function will be Cn, like that. So here only restriction on V is that such that however, do remember this dot indicates always with respect to time we are differentiating, right? With respect to time we are differentiating. This v dot x in entire omega we are having this. Now let let m be the largest invariant set in E, then every solution starting in omega approaches m as t tends to infinity. So let us quickly just see the statement of the theorem. Omega belongs to D. So which D we are talking about? Of course that D, that our very own D, where we have fx is a Lipschitz function with respect to x, right? So in that domain we are having a compact set omega, capital Omega, that is positively invariant for this autonomous system x dot is equal to fx. Then we are taking V, a function that is having continuous differentiable function V, such that V dot x is less than is equal to 0 in omega. Now let E be the set of all points in omega where V dot x is equal to 0. Let M be the largest invariant set in E. Then every solution starting in omega approaches M as t tends to infinity. So what it try to state, and like how to understand this, what, just a minute. Okay, so let us take an example like what? Now let us take this example where my favorite example, x1 dot is equal to x2 and x2 dot is equal to that equation of mass spring damper. So what you will observe that for a positive value of now, if you define Vx is equal to half x1 square plus half x2 square, then you will see that Vx comply with our requirement here. Like nobody claims that Vx cannot be positive definite. It is nowhere mentioned. It is nowhere mentioned that Vx cannot be positive definite. Only requirement is that means it is a more generalized case where Vx can be positive definite or cannot be, but Vx must have a continuous first like derivative and it must be continuously differentiable. Now see what we can write here, that v dot x will become so. Now again you will see that it states v dot x is greater than is equal to 0. So everywhere in this case the entire plane will get v dot x less than is equal to 0. Now let E be the set of all points in omega. So here our omega is that entire region, and points in omega where v dot x is equal to 0. Actually, as I have taken a linear equation, it is easy to understand the entire space. This equation will be elliptic, right? Like everywhere you go, it will be elliptic. No matter wherever you take, your entire R2 is your D, and that entire R2 is your D, and that omega is also the entire D. Now here this v dot x is equal to 0 is where v dot x along this x2 axis, your v dot x is equal to 0. So this is your E. By definition, E is the set of all points in omega where v dot x is equal to 0. Let M be the largest invariant set in E, then every solution starting in omega approaches M as t tends to infinity. So what is the definition of invariant set? That if your solution means any solution cannot leave the invariant set. We know here in this case the only invariant set is this one, like the origin, right? But like why this is also important, like let M be the largest invariant set in E. So M contains all the points. Here M contains only one point, but in some cases it may happen that M contains all the points. Like if I just how to explain it, like if I make it a frictionless system, then what would happen? This would be dropped. Well, so this x2 dot will be minus k by m x1. So if we do it, we will get what? We will get something x1 x2 minus Sorry, I think in the previous case also I made a slight mistake. Let it be half kxm square. Yeah, this will, yes, previous case it was like when it was minus b by m x2, it was minus b x2 square, and now if I make this is equal to 0, like if you make b is equal to 0, then the second term will become 0. Then what you will have here, you will have this v dot x is equal to 0. Irrespective of any x1, x2, it's 0. So what you will have in that case, like, then obviously one confusion will arise. Like then not only the entire plane will become E, isn't so? Think about it. If you make v dot x is equal to 0, and what is the definition of E? Is the set of all points in omega where v dot x is equal to 0. So if v dot x is identically equal to 0, then what makes sense? Like all the points will be in E. Then how to define M? That is also a question. I'd like to hear from you. Anyway, let us just refrain ourselves, but instead of making it too generalized, and let it be this only. So this is clearly a negative semi-definite one, but our experience tells that it is also a case of asymptotically stable system where typically our solution trajectory takes this form. Now, obviously, for a given means this E M means we have to prove that v dot x, let M be the largest invariant set in E, then every solution starting in omega, like anywhere it starts, it will approach to this particular M. Like in other way, we are just trying to state that for this case it will become an asymptotically stable system. So let us go for the formal proof of this one. So what we can see that let a generic solution, let xt be a solution like how a solution can start in omega. If your initial point is in omega, then only the solution starts in omega comes in the picture. Otherwise, if you take your initial point far beyond the region omega, then there will be no point of lamenting over it, that why it's not happening or this that. Now since what we know that v dot x, so it is clear that Vx with respect to t. Now here I would like to highlight that subtle things that may cause a confusion and may again can be solved in other way. Like in case of Lyapunov, we know that Lyapunov function has to be positive definite. So Lyapunov function is bounded below. But here, if we see, we have removed that restriction that Vx is not required to be negative definite, and you are saying that Vx is a decreasing function like v dot x less than is equal to 0. So less than 0 is also a possibility, and it can be very aggressive means aggressive negative, or means very high rate of change you can have. But what is the beauty of this definition of omega? That omega is a compact set. So when omega is a compact set and you are having that Vx is continuous on that compact set, so we know, although I wouldn't manage enough time to show you the formal proof, but what we know that on a compact set, and now I told you several times, but I couldn't show you the formal mathematical rigor or mathematical proof of this means in favor of this statement, or means justify that statement. But we can intuitively figure it out. Like what we know, that what is a compact set? Compact set is a closed and bounded. Like all the points on a compact set is closed and bounded. Now, you may ask me the question that, sir, this V is continuously differentiable with respect to t, but it has nowhere mentioned that how it is related to your, like, this continuously differentiable function V. It is means how to relate its, like omega is defined on with respect to x, right? Your plane is what? Your plane is plane comprises state variables, right? So omega is compact with respect to that, and on that compact set you are defining a function that is also a function of the state variables and implicitly dependent on t. However, evaluation with respect to t, like if you do it, what you will get, like dv dt will be what? right? So we are saying this is continuous, means this is continuous. So obviously, now I'm not going to give you the exact proof of this one, but just try to understand that why I am claiming that continuous on a compact set and the function is having negative or zero rate of change with respect to t, then it is must be bounded from below on omega, like function cannot cross a certain value of b dot x. The answer here is that it's very simple, like your these things is continuous, right? Like del b del t, del b del x x dot. Now on this omega, how you define omega? You said it is a compact set, but omega is a subset of which region or which set? That is D. What is D? D is something where fx is Lipschitz. What is fx? Fx is the rate of change of x dot. So basically here you can write it is fx. So that one was what? That one was Lipschitz. And this omega is compact with respect to the elements present there, like this. So obviously this function cannot have anything like any, it cannot have an abrupt negative change. It must have a bounded variation within that region or on that region. Means I do not know how much of you can relate or how many of you can feel or how much you could relate, but try to understand. Otherwise, after this completion of this course, I will give you the formal proof. But this very beautiful thing that we are not mentioning that Vx is positive definite, but we are claiming that Vx is bounded from below on omega. Now, what is the that bound we are not discussing here yet. So now think about the second, means if we further proceed, then we will see that now what we know that positive limit point set at positive, this L plus is what? That is positive limit set is also in means omega. Now for any point P belongs to L plus, again we have reached the end of that for any P belongs to L plus. Now think about it, that we can again have a sequence Tn sequence Tn and this xtn tends to p as your n tends to infinity. Now as your Vx is continuous, so Vp will be what? This is equal to, let it be a point A. So here this Vx is equal to A on L plus. Now this L plus is an invariant set. Like if we go back to our previous lemma that I toiled a lot to prove. What was that lemma? If a solution xt of x is equal to fx is bounded and belong to D for t greater than is equal to 0, then its positive limit set L plus is non-empty, compact and invariant set. Moreover, xt approaches L plus as t tends to infinity. Right? This was the lemma. So then by this lemma, V plus is an invariant, means L plus is an invariant set, and if L plus is an invariant set, what you will have? Any trajectory that will always stay in L plus. So how it can stay at L plus? It must be thus what you can write. So since xt is bounded, xt approaches hence we can say that like this could be means not only a proper subset, it could be an improper subset also. So what is the additional thing here is that omega, this set omega has nothing to do with construction of Vx. Here in means like in many applications you will see that Vx means construction of Vx will itself guarantee omega on which it is continuously differentiable. Now just let us see that how we can apply this on some problem. However, before applying this LaSalle's invariance theorem, we'll study two corollary that are immediately the inferences can be drawn from this invariance theorem, right? One thing that I have already mentioned before going to the theorem, let me show you one example that proves that how this omega that is actually related to this omega c construction, it's itself related to Vx. One thing that is quite obvious that omega c region in your xn is always bounded when we take two things like okay, so the bounded is always bounded when Vx is positive definite. But it is not bounded in other cases. Like, let me show you some cases. Like, let us take two examples. One is, rather three examples. One is another one is third one is for this first one. You can see that all the things like if you take an x within this region where is like, then you can have a case like here, sorry, this is the region where this holds. So it is now how to define a region where Vx is positive definite. Clearly Vx is positive definite when this holds true. Then you can map it in that corresponding and you will get a region here. Now for the same thing, if we try to do it for this function, you will get what? Say Vx is less than c. So Vx less than is equal to c means here you will have something a region like this. And inside this you are having your Vx. And for this one, this is clearly a radial unbounded. So you will have the entire plane. But this is somewhat bounded. Whenever you are talking about some Vx, then you will always get, for some finite c, you will always get a circle inside which you are having x1 square plus x2 square is equal to root c. So this is all defined means region. So you can understand that omega c is bounded whenever you are considering a positive definite function. It may be positive definite over a certain region, or maybe positive definite over the entire plane. But whenever you take positive definite, then omega c becomes a bounded region. Now, before as I told you that let us discuss the which is known as Barbashin and Krasovski's theorem. So that Barbashin and Krasovski, they means have proved and drawn these inferences well before LaSalle did it, but means as LaSalle's one is more generalized, so we now state LaSalle's first and then we state Barbashin and Krasovski's like the two corollaries of our LaSalle's theorem. So what Barbashin states that let x is equal to 0 be an equilibrium point for x dot is equal to f of x, let be a differentiable function on a domain over that domain let S be a solution not and moreover this triple equal sign means it is identical equal to 0 can stay then the origin is asymptotically stable. Actually, this is what is means what we have observed for our that mass spring damper. All these points where this belongs to S, but only the trivial solution that can identically stay in S. All these points, if you pick up, all of them will become a member of S, but they cannot stay in S because in order to stay in S, you have to satisfy v dot x is equal to 0, and this trajectory as it is momentarily just staying there, and after that you for very instance it again started moving away from that point, we can say that it is identically belongs to S. So this is Barbashin, and that only one point Krasovski is contributed, that if we find that this Vx, whatever we have studied here, is like radially unbounded. So what is radially unbounded? And that I will discuss in two examples, like 1 minus x1 minus x2 square, that is positive definite within a particular zone, that is not no way radially unbounded. But if you consider that your x1 square plus x2 square, that is a function that is true sense radially unbounded, whatever value of x you can take, all the time you will get it is giving you the means positive definiteness. So that's all. Now we will solve a few examples, and then we will discuss next. Is will move towards non-autonomous systems. Let us consider that problem. We are having a system x1 dot is equal to x2, and your x2 dot is equal to minus h1 x1 minus h2 x2. Oh God. So here h1 and h2, only thing mentioned about h1 and h2 are that they are locally elliptic near origin and satisfy hi 0 is equal to 0 for I is equal to this, and y sorry and tau h tau is equal to tau hi tau greater than 0 for all tau not is equal to 0 and tau belongs to this open set. So the system, it is clear that the system has an isolated equilibrium point, at least in this region where you means the region is bounded by a circle of radius small a. Within that region, you cannot have something like your means only equilibrium point will be 0, 0. So here we can define our Px and Lyapunov function and energy like function. So you will get something like if you let this D be such that actually it is not means uh, defined by a circle, rather a square with sides, right? So if we have Vx is positive definite in D, then if you find out V dot x, you will be able to understand that V dot x will become so it is clear that means everywhere it is negative semi-definite, right? So if it is negative semi-definite, let us find means if we try to apply that means Barbashin Krasovski lemma, then let us find that what happened if we define S. Basically, S is here very clear. S is the line on which x2 is equal to 0. You are having D such that now V dot x is equal to 0 implies what? Now the solution now is it is like we have this is let xt be a solution that belongs identically in S. So identically in S will implies x2t identically equal to 0, and that implies zero. So that implies each one from this equation we can write that this implies each one x1 is equal to 0. So it is clear that the only trivial solution can identically stay in S, and thus the origin is that's it. Now if we can just like expand this region from previously we consider it minus a to plus a. Now if we expand this region to minus infinity to plus infinity, actually we are trying to consider the entire means R2 plane. Previously it was a square of shape here. Previously it was like this. Now if you make a is equal to infinity, then what will happen? This square will like grow and then it will cover all your x2 plane. Now we can show that If this satisfies, then what we will have? We will have in addition, if we can have a condition like then the second part of the first function like the function which we have will become radially unbounded. So using this you can again show that only the trivial solution or the origin is can identically stay in S, right? Now let us take another example. Like first order system. Here the control law is adaptive in nature. Instead of fixed control law, we are using an adaptive control law, where K is the adaptable gain parameter or mutable gain parameter with gamma y square, where gamma greater than 0. It is the means parameter gain rate. Now if we take x1 is equal to y and x2 is equal to k, then we will get x1 dot is equal to, from this model, if we put this expression of here, we will get so clearly this is a nonlinear system where what is your equilibrium point? Your equilibrium point is x1 is equal to 0. Now what is our objective? Our objective is to show that the trajectory, means any trajectory, approaches to this equilibrium as we set t tends to infinity, which means that the adaptive controller is able to regulate y to 0, right? So here we are having two parts. One part typically the x1 part, that is related to your system variable, and another part that is related to your parameter convergence, that is denoted by x2. So always in case of adaptive system you should define it like Vx half x1 square plus 1 by 2 gamma x2 minus b square, where your b is greater than a. So why this is necessary, I will discuss, rather you will understand when we will proceed with the derivative. So what you will get, that if you do this v dot x, you will be having v dot x will be having x1 dot plus so if you put the values, eventually it will result you minus x1 square b minus a less than is equal to 0. That is why this, due to this b minus a part is coming, we need to take b greater than a. Had we taken a or something else, we may have a confusion, right? And you may say that why it is necessary at all, like why can't we deal with like direct x2 dot. Answer is that, like, if we take, what would happen if we take half 1 by 2y x2 square, that will lose any control over our parameter variation. Anyway, so what we are trying to show you here, that is v dot x less than is equal to 0. Now clearly the way we have defined vx, it is radially unbounded, right? Radially unbounded means it's totally means if you increase x1 and x2, it will reach infinity. Now your set where x is equal to like what to say, like that set I'm talking about, that omega c. How to define omega c? Omega c comprises all point in R2 such that Vx less than is equal to c. So as Vx is positive definite and means radially unbounded, so you can understand that this is a compact and this omega c is going to be a positively invariant set. Now taking omega is equal to omega c, that all the conditions of our LaSalle theorems are satisfied. Now let us write the set E. How or what would be the construction of E? The set E, what was that definition of E? E contains all the point where your v dot x is equal to 0. So v dot x will be 0 when you will make x1 square, means x1 will be 0. So the set E is given by E is equal to x belongs to this, such that, or better to write x belongs to this omega c, such that x1 is equal to 0, right? Now this any point on this line x1 is equal to 0, if you means understand this problem, then you will understand that any point at on x1 is equal to 0 is an equilibrium point, right? Where x1 is equal to 0 is an equilibrium point. Actually x2 is here, x2 is related with parameter, not with it's a system variable. System variable is x1. So whenever your system reaches x1 is equal to 0, the system regulates to 0. Basically it means it has achieved its goal. Irrespective whether you have something or not, the parameter means mutation rate automatically boils down to 0, right? That is the very interesting things, and that is why I picked up this example. So you can see that your system is like a global asymptotically stable system. right? So in our next lecture we'll discuss, or we'll extend our discussion to non-autonomous system. As of now we were discussing only autonomous system. Next lecture onwards we'll discuss non-autonomous system.